Hello everyone, welcome to the lecture number 39 of this NPTEL lecture series on charging infrastructure. And in this lecture, we will study about the small signal modeling of phase shifted full bridge converter. In the last lecture, we have studied about the phase shift full bridge operating modes of phase shift full bridge converters. We saw that in total there are 6 operating mode 0, 1, 2, 3, 4, 5. There are 6 operating modes, and which repeats itself when this will be the same for the next set of diagonal switches. Here we were in this we have seen diagonal switches S1 and S4, and then we have seen the diagonal switches S2 and S3, how they actually turn on and off. And we have also seen that how, because of this presence of this output capacitances of the device and this L leakage, this transformer, how we can achieve using these two combinations or using these two parasitics, how we can ensure we have a ZVS of turn on of all the leading leg switches. These are leading leg switches and lagging leg switches. We have seen that, and we have derived the different aspect regarding to them, the dead time requirements, which ensures that the body diode of the MOSFET gets turned on first before the gate pulses are given to, or before the gate pulses are given to form the channel in the device. Now because of that, diode turns on, the voltage across the device is actually 0, and that is when we will achieve the 0 voltage switching during turn on. And since we are getting a 0 voltage switching during the turn on, that means the diode turns on, that means the output capacitance discharged by the output current which is coming out of the half bridge. So because of that, DVDT at the output of that bridge is actually limited by the charging and discharging of the output capacitances of the devices in the particular leg. Now we have seen the primary current, which is nothing but IL, NIL, which is the reflected part of the inductor current. Then in this part again we have this NIL which is there. In this part here again it is NIL which was there, and in this period it was actually the IP will be because of the resonating of this particular leakage and the lagging leg switch capacitances. And then after that we have seen that the current will fall down and doing the zero crossing, and then it will keep on going in that way. Here we have the slope which will be defined by minus V in by L leakage. The slope is done in such a manner that till the point it reaches the point where the IP is equals to NIL, or the reflected current from the IL. So here it is again NIL which is coming over here. So till that point, the output rectifier which is applied across at one end of the output inductor, the voltage is still 0, and after that only the voltage of NV in will be applied across the one end of the inductor. And then we have seen that if we look very carefully, these are the different modes. In mode 1 my S1, S4 and DR1 is conducting. In mode 0, in mode 1 the C1, C2, the output capacitances of the switches S1 and S2 in the leading leg it is conducting. Then we have the diode DR1 and S4 switch is conducting. Then so here it is we are doing the changeover of leading leg switches, changeover of. Then in mode 2 we have seen the D2, S4 and DR1 is conducting. And then in after from the mode 2, since the D2 is conducted before the gate pulses of the S2 switch is been given, so the S2 switch will achieve the ZVS turn on of S2 switch. So to do that we must provide some sufficient dead time, and that dead time was nothing but 2 CV in by I1, where C is nothing but equal to C1, nothing but equal to C2. Then in the mode 3, that which occur when you remove the gate pulses of the lagging leg, so changeover of lagging leg switch. Leg switches is taking place. So during that time again my S2 and then C3 and C4 is actually discharging and C3 is charging, and then because of that here the voltage across the A and B will be minus of Vc4, and since Vc4 is discharging, so the voltage VAB will be discharging, as a result of which the IP will be less and it falls short of the actual output inductor current, and that's when both DR1 and DR2 gets conducting, and as a result of which what will happen is that from the secondary side of the transformer is completely short circuited, that means primary side of the winding, I mean primary side voltage is also 0, and all the VAB will be coming across the L leakage, and as a result of which L leakage goes to resonance between, here L leakage is actually doing the resonance with, resonates with C3 and C4, and that's when you will have, because of the resonance, that if we have to provide sufficient amount of time for that resonance in which this capacitor get fully charged or discharged. So for that we have seen this particular scenario that we have to provide a dead time for the lagging lag, which is we have obtained in this manner. Now after this kicks in, what happens is that, let us say we have given sufficient dead time such that the voltage of the VC4 goes to 0, and that is when the D3 will get conducted, and then after some time, since the D3 is conducted, you can now give the gate pulse to S3, and that is when we can get the ZVS turn on of S3. So we have moved from S1 and S4 switch to S2 and S3 switch, and then after turning on S2 and S3 switch, the IP or the primary current will keep on going in the negative direction such that until it reaches this point when IP is equal to NIL, until the IP is equals to NIL, we will keep, it will keep on going, and during that time this so DR1 and DR2 is still be on, because output inductor current has to find a pathway, and then after mode 5 my IP is actually equal to NIL, and that is when my entire changes, entire finally this thing will take place here. So if we went from S1 S4 DR1 to S2 S3 DR2, and we see that from mode 2 to we can say mode 5, till this point from mode 2 to mode 5 there is something duty loss which is taking place during that duration, and so we can say T2 to T5, because this kicks in at T0, this kicks in at T1, this kicks in T2, this kicks in T3, T4, T5, and if you see T5 we have the T0, no sorry, this kicks in, T0 kicks in, T0 was before T0, this one kicks in at T0, if you look very carefully, yes, mode 1 T0, mode 1 T0, mode 2 T1, this is T2, this is T3, this is T4, and this is kicks in at T5 point, I mean the time period. And because of that what we will see is that from T2 to T5, which is we can say mode 3 to mode 5, so we have the duty loss from mode 3 to mode 5, that means time T2 to T5, this duty loss will be there. Similarly, we have also seen what is a necessary condition for the ZVS to happen for the lagging leg switches and the leading leg switches, and that too during turn on period. We have seen that for the leading leg it is the output inductance which is a very large in value, that is actually coming in series with the L leakage, and we can say that I1, which is actually the current reflected from the output inductor which is coming into picture, and that energy is actually being utilized to discharge the C2 and charge the C1 capacitance to either V in voltage and or 0 voltage, and that is where we can say that this particular condition is true even if this I1 is small also, it is true. So we can get 100% GVS for most of the load range. However, for the ZVS turn on of the lagging leg switches, since the energy from the capacitance of lagging leg switches is been getting taken out by current which is flowing through the L leakage, and only L leakage is coming into picture. So this value becomes very critical, because at less load condition, less loading condition, when the IP is very small, this energy is actually very small, and that is when which is not sufficient to actually discharge the C3 capacitor and charge the C4 capacitor. So that is why these are the conditions, and this may or may not happen, this this particular ZVS turn on of this may not happen at the light load conditions, or when generally when you have smaller leakages and when you have good amount of larger value of C3 and C4 and larger input voltages are there. Then we have seen the duty loss, as we know that from T2 to T5 there is some amount of duty loss which is happening. Now we have finally derived the duty loss expression, and which is, this duty loss is actually related by L leakage, Ni naught, Fsw and V in. Where D loss will come into picture, because we have V naught is equals to N V in, D minus D loss will be there. Again, how we can get the duty ratio? Since we are doing phase shift, so we have the phase shift which is between T0, or you can say between T2 to T0 period divided by Ts by 2 for 180 degree, and this 1 by D period, 1 minus dTs period by 2 period, you can say that it is roughly the period of delta by 180 degree Ts by 2. That means if you increase the delta value, you will actually reduce the output voltage. So since it is a derived topology, if you look at the output part of this circuit, it is nothing but same as the buck converter, LNC and then RL. So what we can say that it is a buck derived topology, that is why our V naught is N V in times D. However, because of achieving this ZVS operation, what happens is that we are actually losing some of the duty ratio, and because of the presence of this capacitance and the inductor, we are losing some of the duty, and we can say D effective is actually nothing but D minus D loss. So what we are trying to do, we can say that if we write down this thing, let me write down this thing, is D loss is nothing but equal to 4 L leakage N I naught Fsw divided by V in. So we can say that my V naught is nothing but N V in times D effective, and my D effective is nothing but equal to actual D which you are applying, which is corresponding to phase shift which you are giving, minus D loss which you are actually losing out. So this is what we were seeing, this D effective, and this D effective, if you look very carefully, this D effective is actually related to L leakage, we can say, and this we can also write this D loss in more generalized terms as 4 L leakage N IL Fsw by V in. We can write in that way, because we assume that the average value of inductor current is nothing but equal to the which is going into the load. So we can say the average value of inductor current is nothing but the output current, so we can just write N IL. Now we can say that the D effective is dependent upon the L leakage, it dependent upon the Fsw, the switching frequency, the V in voltage, and we can say that the current through the IL, whatever the current which we have, which is flowing through the IL, which has some average value which is coming over here. So the D effective is effectively dependent upon or related to L leakage, Fsw, V in and IL. That means when we are changing these 4 values, our D loss changes, and that is when our D effective also changes. Now if we have a circuit, or if we have the actual hardware circuit, the L leakage and Fsw is not gonna change. Since the L leakage and Fsw is not gonna change, we can say that the D effective is kind of independent of there is no change which may occur due to the L leakage and Fsw. However, during the circuit operation or during the operation of this converter, we will see that this V in may change and IL may change, because suddenly there could be a transient which changes the V in voltage and the average current which is going through the inductor. You can imagine, let us say suddenly the load changes, so your IL value also changes. Now if those things changes, so if V in changes and there is some IL which is actually a small change in the IL which takes place, so what you will see is that you have the D effective, we can just write D effective in a smaller, this one we have a D effective will also change. So in this phase shift full bridge converter, what are the control objective? Now control objective is, if we see the control objective is only one, which is to regulate the output voltage as per the reference. So, it is to regulate the output voltage. Now, in this converter, if you see the converter, so in this particular circuit what we have here, we have the output voltage V naught and we have IL current going in. Now, if you look very carefully, this output part of the circuit, which comprises of this L, C and RL, this particular part of the circuit, output part of the circuit, is similar to that of the buck converter. If you recall the buck converter, we have one switch, we have the diode, and at the output we have this RL, C, L, diode D and switch S. This is the buck converter. If you look very carefully, the output filter stage of both the converters are nearly same, and that is why we can say that this is the buck derived topology. And if we see the output voltage, we know that our output voltage is nothing but N V in times D effective, it is D minus D loss. And if we see, if we wanted to regulate the V naught as per the set value of reference, what we can change? We can only change this duty ratio D. The moment we change our duty ratio D, the VR voltage will change, and if there is a VR voltage change which will be taking place, what happens is that this current through the inductor changes, and because of the current through the inductor changes, the capacitance voltage also changes, which actually determines the output voltage. So, here if we see, the moment you change the duty ratio to regulate the output voltage, the moment you change the duty ratio D, what happens is that your IL changes, and since your IL changes, your V naught also changes. And if we see very carefully, the moment my IL changes, my D loss will also change, or I mean let me say in the small signal manner, if there is a change in the duty ratio or this thing there, and my D loss will change, and since there is a D loss change in there is some change, effective change due to the current change in the IL which is coming place and which is actually gets added up over here. So, what we can say that my D effective will be nothing but the change which has to occur to make sure the output voltage is controlled. This duty ratio has changed. Along with this, there is another term which is DI, which has occurred, this extra change in the duty ratio which has occurred because of our D loss is changing, and this D loss is actually lead to the change in the D effective, because our D effective, we know that our D effective is nothing but D minus D loss. So, the D effective is actually changes with the D, and along with this our IL changes, and because the IL changes, there is change in the D loss, and that D loss will also come along with this D. And if there is a change in, if there is a change in the V in voltage, so in order to make sure the output voltage regulated, even if there is a change in the V in voltage, the D changes, and again if the D changes, my IL changes, and along with IL my V in voltage is also there. So, we can say there is also the dV which is coming into picture, where we can say that DI is the change in the duty ratio due to change in inductor current. And how this change in the inductor current takes place? It is because you are actually changing the duty ratio of, you can say, VR voltage which is coming over here. I mean the time for which the VR is non-zero. So, that has changed, and similarly we have dV, which is change in the duty ratio due to change in input voltage. And because of this change in this thing, our D effective changes, because D effective is obviously because of change of a duty ratio, this is changes, and along with this we have DI change and DV change as well. So what we are trying to do, in order to ensure my output voltage is constant, we are changing the duty ratio. Since we are changing the duty ratio, our D effective changes, and since our duty ratio is changed, our the duty ratio, what we can say, duty ratio is the time during which the VR, in the fraction of the time during the Ts by 2 period when my VR is non-zero value. So during that time my IL changes, and because of the IL changes there is a change in the V naught, and because of the IL change there is a change in the duty loss, and that is actually corresponds to the DI, and that DI will now get added up to this D to have defined the effective duty ratio D. So now let us see how we can, this two extra term what we have, how this will impact the response. See, you try to understand this. When duty ratio D changes, VR voltage changes, and then the inductor current will respond to the change in VR with some dynamics, which will then get reflected in capacitor voltage with some dynamics, as capacitor takes some time to respond to this change. Further, with IL change there is change in D loss value, which will further change the effective duty ratio, which corresponds to the Di tilde term, and thus Di tilde term has to be added in the effective duty ratio to see the effective dynamics. Further, when input voltage changes, the D loss changes, which impacts the duty ratio. So, the dV tilde term also need to be added to see the effective change in the duty ratio, which is defined in D effective. So, the dynamics in the D effective is the combined dynamics of D, Di and Dv. So, we can say that the dynamics in D effective is the combined dynamics of due to change in D, and along with that D, the Di and Dv. Now let us try to see, or let us try to find out how my Di will look like. Now let us see how we can say how our Di changes. So effect of Di, small change the Di. So let me try to draw the Di effect of Di. Okay, so let us first see IP, and then we will also see VAB here. So IP was rising, nothing but with NIL, whatever the output inductor current is, that got reflected here. Then from here to here it goes down like this, from T0 to T1, then from T1 to T2 it falls down again, and at the same time my VAB was at V in, and from V in it goes, after this point it goes to actually 0 with slanting this thing, and from there it goes to 0 here, and at T equal to T2 my S4 switches turns off. Because of that there is oscillation is there. During this time my VAB will rising like this, and it goes to minus V in, at last. And after this what happens is that, if you see here, my V in is actually goes to minus V in over here, and at that point we will see our current is actually linearly rising up till goes to 0, and then finally it goes to T5, where again it is V0, it is there, and then it continues its operation. Similarly, we can also draw our one more thing, which is our VR. If we try to draw our VR, so it was here, it was NV in, Here again it was following the VAB, and after this it goes to 0 here, it goes to 0 here. T0, T1, T2, T3, T4, it is 0 here, and it again goes to 0 here, and at that point, and that's when it goes to here NIL, it has volt. If we look very carefully in this side, what happens is that the moment at this point when the DR2 turns on, the VR voltage is nothing but again goes to NV in, and this is again minus V in, which was there from the VAB. Now if you see there is a fixed change in the IL, assume that fixed change in the IL, if we just take this one here, we can just write NIL is here, and here let me write here it is NIL here. Here also it is NIL, reflected part of NIL, here also it is reflected part of NIL. However, in this part it is not the reflected part of NIL what we have. So now what we can see is that if we see there is a fixed change in the inductor current, what happens is that we will have the fixed, let's say this is a fixed NIL change we have incorporate here. Then we can have something like this here. On this side we have the same thing coming over here, same thing coming over here, and what we see is that beyond this point we will see that our this part goes like this, and from here it actually follows, and it goes here, and then it follows like this here. This part goes over here, and then it follows from here. Now because of that, what happens if I try to draw the things VAB over here, so it will follow the same line, same thing, same goes over here, same thing over here. However, the moment this point reaches to NIL, at that point only my this VR changes. Now because of that, this is this time which is defined as the delta T, which is actually lead to effective change in the duty ratio. So this delta T corresponds to change in D effective due to change in IL. So we have given the change in the IL, and because of that we have change in the duty ratio, effective duty ratio. Now if we look very carefully, in this period of time, it changes from this period to this period. This is the time. So the slope goes from this point to this point. So let us try to write the equation corresponding to that. If we are trying to write the equation, now if you look very carefully, this particular slope is actually coming across the L leakage, and if we recall our expressions for that, we know that it is nothing but our, if we try to, because here it is T4 and here it is T5, is T5. So we during T45, if we write T45, if we write T45, if you recall our T45 is nothing but L leakage, we have N IL at T5, and that is nothing but NIL T5 divided by V in. That is the value we got between T4 to 5. And if there is a change here, if we see over here the changes is there, if there is a changes here, so we can write down, see this changes is happening from this point, going from this point to this point, during from this point to this point. So we can say during the unchanged time it was at this value, and during this change happens twice the value. So we can say that the T45 new will be nothing but L leakage N NIL, plus if we take this as from this point to this point, if we try to recall, it is nothing but 2 times of that. So we will get, so this T45 new will be is NIL plus N delta IL, or you can say the change in this delta IL, if we say, or you can say N IL goes to this one and delta nu, and the previous one if we do from L leakage divided by V in, and if we think we take the old using this particular thing, we can just write L leakage, because from this point to this point we can just write N IL, because here we have given the change, so minus N delta IL by V in, and then we can write delta T to be L leakage 2 times N, not it is not delta IL, it is N IL we have written here. So N IL, small N IL we have. So it is 2 times N IL, small IL change divided by V in. Now because of this thing, whenever there is a IL change in the output inductor, it gets reflected in terms of NIL. So there is the effective delta T change is nothing but L leakage times 2N the IL, small IL tilde divided by V in, and then we can write that change in the DI, we can say that it is nothing but minus delta T by Ts by 2, which is actually, if we write down from this term, it is minus L leakage by V in 2N IL Ts into 2. Now that is nothing but comes out to be minus 4N L leakage, and we can then write F Ts to be F switching frequency divided by V in times IL. So because we know that our Ts is nothing but 1 by Fsw. So we will finally get minus 4 and L leakage F switching by V in. Now this is the Di. So we can write finally Di, change in the Di is nothing but minus 4 and L leakage F switching, small change in the IL divided by V in. Now if you look very carefully, you will be wondering why we have taken the negative sign. The negative sign is taken because if your IL increases, let us say your IL increases, if this IL increases, so what happens, this distance will also increase. Because of this distance increase, what happens is that you will see more, at that point it is coming. Now because of that your delta T is actually reduces, because the effect is opposite of cause in this case. So because of that, since here my delta, since my with change with when IL increases, my delta T reduces, that is why the negative sign is used. And now if you look very carefully, so finally we got the, whenever there is a change in the IL, how that particular impact because of the change in the IL is being captured, and this D will be added with the effect captured due to the actual change in the duty ratio, and this in the actual change in the D effective. So this is the additional term which will be additional dynamics which we will see whenever we are changing our duty ratio, because when we are changing our actual duty ratio D, our VR voltage changes, and because of VR voltage our IL changes. Because our IL changes, there is another addition in the inductor current will take place, and because of that there is more loss in the duty ratio, and because of that the D effective will have further changes. So let us see our effect of dV, that means whenever there is a change in the input voltage, that means due to change in input voltage. So during that time how our thing changes. So let us see how our thing changes. Assume at this point our input value changes like this value changes. So as a result of which what happens is that this value what we have seen is there will now be slightly changed. So we will see how things will go. So now if you look very carefully, this particular slope, if we see, this particular slope is nothing but V in by L leakage. So this slope is actually gonna change, and that we can write down. Since my V in voltage has increased, so our slope will actually be increased. So what we will see is that our change in the slope changes, and actually it reaches to this IL value faster. And the moment it reaches to IL value faster, after this will be flowing like this. Now because of that, what happens is that since our slope has increased, the slope which is actually falling down, which this is minus V in with the minus V in by L leakage slope, it is falling, and since my V in voltage has increased, so that's why my slope has increased, and that's why you will see it will fall down faster and reach to this IP, where which is equal to the reflected value of IL faster, and as a result of which we will see in our this period, so this will be the same like this. However, during this point when this thing happens, so this will actually be going over here, and it is with slightly increased V in. We can just write, so if we see, so if we say this is NV in, so our new will be, this will be our this new will be NV in plus NV in tilde, and this small change is nothing but your NV in tilde, which is a small change in the V in voltage we have given. So because of that, now if you look very carefully, this is the additional time which has actually reduced, since our V in will have gone through that. So this value is nothing but equal to delta t. Now from this term, if we see very carefully this particular term, how it will look like. So in this particular thing, we can write down this delta t, period. If you recall, during this point, from this point to this point, we have seen that it is nothing but, so if we assume T23 to be very very small, then we can just write. Now if we assume T23 to be very small, then we can say that this point and this point is very much near to each other. So if this point is NIL, which is coming over here, the same NIL will also be coming over here as well. So we can say that if this is small, so we can say that our delta T to be equal to, we can just use the term V is equals to L di dt, and the dt we can take it up, so which is nothing but your V in by L into di. So to write down this particular expression, the delta t expression, so before the delta t at during this time, we can just write, this is the assumptions we have taken. So because of that, we can write it is nothing but NIL, we can write NIL which was there previously, and at that point it reaches to this point, we can just write minus of minus NIL, because this point you have again reached to minus NIL value. So this is also minus NIL, so minus NIL, and plus there is this ripple which gets ended up, and then again it is going up. So this we can write V naught by L 1 minus D Ts by 2. This value what we have taken, this V naught by L 1 minus D Ts by 2 is due to ripple in the output current. This will also be multiplied by N, because we have this is the reflected part on the primary side, so this is a ripple in the, is due to the ripple in the output inductor current, to be more precise, inductor current. Now this is the our di terms, and then what we have is our, we can say it is nothing but, now we have our L V in voltage which was there previously, L V in voltage, because L V in which was there, minus L V in plus V in tilde, which is the change in the inductor, and this is due to the change in the change in V in. So it was before the change in V in, and it was after the change in V in, and that we have subtracted to obtain this particular expression. This is, so L leakage is here, this is L leakage is here. This L is the output inductance, this is the due to the leakage, this is L leakage which we have written over, so it's the inverse of the slope here. Now because of that, if we do the simple mathematics, so we will get delta T to be 2 n IL, and now this IL will be the average value we can say, and we can just write directly 2 n I naught here, and that will be plus, because this average value, this we can just say that this is the average value we will, because this is at this places the NIL which was reflected is nothing but the output current, and that output current we have already assumed to be nearly having a zero ripple. So this we can write 2 n I naught, and that will be nothing but equal to minus n V naught by L 1 minus d Ts by 2 period, and this will then be, we can write down V in times V in plus V in tilde, and this will go up and up, V in get cancelled, so it is L leakage V in tilde. This is the term which we get, and just also change in V in, and this we can easily write like this. Now this particular term we can then further simplify, and then we can write down delta T to be, and we can take it out, we can write 2 I naught minus this term minus V naught by L 1 minus d Ts by 2 this will be L leakage V in tilde divided by V in multiplied by V in plus V in tilde. Now if we look very carefully in this particular expression, what we can say, that we can also say that this, since our V in tilde is a small change, that means we can say V in plus V in tilde is actually nothing but equal to V in. That's when we can just say delta T to be equal to n 2 I naught minus V naught by L 1 minus d Ts by 2. This L is the output inductance value. This is L leakage V in tilde divided by V in square. And this particular term, let's say define as a 1. So since we have obtained the delta T, so that implies my duty ratio due to dV, a change in the input voltage, effective duty ratio will be equal to delta T by Ts by 2, and that will be nothing but n times 2 I naught minus V naught by L 1 minus d Ts by 2 L leakage V in tilde or V in square, and this is we can just write V in tilde divided by Ts by 2, and this is something which is due to the change in the impact in the effective duty ratio due to the change in the input voltage, the additional effect due to the change in the input voltage. So we can write that in this particular thing, we can say that our total change in the effective duty ratio is the summation of change in the small change in the duty ratio, and because of the small change in the duty ratio there will be change in the inductor current, and because of that there is again change in the D loss term, and because of the D loss term there is a change in the D effective. However, this change was in the opposite direction, because whenever the IL value increases, the D loss is actually increases. That's when my D effective will be actually reduces. So that's why while deriving my DI we have taken the negative sign. However, in case of DV, if you look very carefully, in case of DV, whenever my voltage increases, this delta T is actually in the reverse direction, because my D loss term has reduced. Since my D loss term has reduced, my D effective term has got improved. So that's why we have taken the positive sign here, and that's when we have addition which is coming over here. So we can say that here the positive sign is due to the fact that whenever there is an increase in the V in voltage, there is a positive effect or there is a positive change in the in the D effective, and thus the overall change in the D effective will be equal to the actual change in the duty ratio which we have introduced, and because of that introduction there is a change in the inductor current which has also changes the D loss and which actually inherently changes the D effective. Similarly, whenever there is a change in the input voltage, there will be change in the D loss, and because of the change in the D loss there is a change in the D effective which is captured in this dV term, and that's when we can say our overall D effective will be summation of these three quantities. So by using this information we will try to derive our small signal model of the PSFB. So whenever there is a change in the duty ratio, how the plant will respond to that change, that transfer function we will derive by defining the small signal model. That we will do in the coming lectures. So thank you very much for patiently listening to this lecture, and we will see you in the next lecture where we will be deriving the complete small signal model of the PSFB converter. Thank you.